Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss the fundamental theorem for divergences. So our topic is the fundamental theorem for divergences. This is our topic today. I will give you the statement first. This theorem states what it states: integral of divergence of some vector field V now volume integral of this divergence of V over some volume mu is equal to the closed integral of V over surface S. This is the statement. You have to understand it first. This theorem has other names also. This theorem is also known as Gauss's theorem. It is also known as Green's theorem. Green's theorem, or simply as the divergence theorem. Right? So we call it fundamental theorem for divergences. We call it Gauss's theorem, Green's theorem, or simply the divergence theorem. Understand it. What is d tau? Remember, we have already discussed volume integral. This left hand side is actually volume integral. We have also discussed surface integral. So this right hand side is surface integral, right? This volume integral, this is surface integral. Now V here is some vector field. That means we have a space, and at every point of that space, this vector field V has a value, right? Now what is this d tau? It is infinitesimal volume element. What is this? It is infinitesimal volume element. What is this dA? This dA is infinitesimal surface element, right? I will explain it further. So I write it. I will rewrite it. So I have divergence of some vector field V, then I multiply it with some infinitesimal volume element, then I integrate it over some volume nu. Now theorem says that this volume integral is equal to the surface integral. But the surface integral is a closed surface integral or surface S. Now we said V is some vector field. This is infinitesimal volume element. Nu is some volume, right? So nu here is a volume enclosed by a surface S. You need to understand. If you take some volume, any volume, for example, it may be sphere, volume can have any shape. Now any volume is bounded by some surface, right? For example, if I have a ball, this ball contains some volume, right? It encloses some volume and it has a surface, boundary of the volume. So every volume is enclosed by some surface, and that surface is a closed surface. Closed surface means which divides the space into interior and exterior. It divides space into two parts, interior to the surface and exterior to the surface if it is a closed surface. So we have some volume V. It is enclosed by some surface S. Now in that space, there exists some vector field V. Now theorem says if you take divergence of the vector field, right, then take some volume element of this volume, right, infinitesimal volume element, then you integrate and you add these things over the whole volume, you will get some result, and that result will be obtained by other way also. Other way is what you do, you find this surface integral is sometimes called flux of the vector field. So what you do, you consider the boundary surface enclosing the volume, and each patch of the surface you dot the vector field there. We know dA is, if we have some surface, to divide that surface into patches, represent each patch by area vector dA, and in case of closed surfaces that is taken as outward normal. Now V will have some value here. For example, let V vector field will be this way at this particular location. Now you dot V with dA, right? Then do similar thing for all surface. You add these dot products over the whole surface, over the whole closed surface. That's my right hand side. This theorem claims whether you do it this way or this way, you are going to get the same value. We will check it. Got it? And another thing I want to emphasize here, what is divergence? Divergence of any vector is a scalar, and how we define it, just a dot product. We know del we treat like a vector. It's a vector operator. It has components dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, right? And if we have some vector field, it will have also some components vx I cap plus vy j cap plus vz k cap. And when we find dot product, we know we multiply the corresponding components and then add them. That means divergence of v will be what? Dou by dou x of vx plus dou by dou y of vy plus dou by dou y of dou by dou z of vz. So I am multiplying the corresponding components and then adding them, right? Now another thing is I want to compare this statement with the other two theorems which we have studied. Remember, we studied first fundamental theorem of calculus. It was like this. It stated integral df by dx times dx a to b is equal to f of b minus f of a. Then we studied fundamental theorem for gradients. Fundamental theorem for gradients. The statement was a to b gradient of t dot dl is t of p minus t of a. Want to make the comparison that will clear your concept. Now I have fundamental theorem for divergences, and it is saying divergence of v, volume integral of that over certain volume nu, is equal to v dot dA, surface integral over the surface enclosing the volume. Now see the pattern. There is a pattern in these theorems. What is this? This actually infinitesimal change in the function, right? That is saying integral of derivative of some function. So is basically here it is derivative. If you take this one separately, integral of derivative of some function, right? From some point A to point B, right? So we have here some region from x is equal to A to x is equal to B. Now we are finding the integral of derivative of some function over that region. Theorem says it is equal to the difference of the values of the function at the boundary. A and B are boundary points of the region. Similar is here pattern, fundamental theorem of gradients. Here we have some path. It is basically a line integral, you know. It is also saying integral of derivative, because divergence is a kind of derivative. It contains derivative, right? Dou by dou x, dou by dou y, dou by dou z. There is also saying integral of some derivative over some path, right? Starting from point A to point B gives the difference of the values of the function at the endpoints. So there is some region, there is a derivative in the region, and there are values of the function at the boundary. Right hand side involves the values of the function at the boundary. Left hand side involves the integral of the derivative of the function within the region. Similar is here. New volume is enclosed by surface S. Now there is integral of derivative of V, because this also contains derivatives, right? Within the volume is related to the values of the vector field at the surface enclosing the volume V or new, right? So it has a pattern. Try to understand it. Now we will do an example to verify this fundamental theorem of divergences. That will clear things for you. So I have an example for you. I will solve that and try to understand. So example is, it says check the divergence theorem using the function, using the function v is equal to y squared I cap plus 2xy plus z square j cap plus 2yz k cap, and a unit cube at the origin. Figure 1. So I have a figure. Figure is like this. This is my x, this is my y, this is z. Just different color for it. Then I have like this. So this is my figure. The coordinate here, value of the coordinate here is 1. Here it is 1. Here it is 1. So it is a unit cube. Unit cube means its edges are 1 unit in length. So along x, it has 6 faces: face 1, face 2, upward face, downward face, front face, back face, right? This face, right? 6 faces, but edge length is 1. So it is a unit cube. So question is like this. This is my figure 1. Question says check the divergence theorem. Check the divergence theorem using the function v is equal to y square I cap plus 2xy plus z square j cap plus 2yz k cap. So I am given a vector field. This is x component of the vector field, this is y component of the vector field, and this is z component of the vector field. So I have to use this vector field and a unit cube which is placed at the origin. I have to use it to verify the divergence theorem. Now what is divergence theorem? I write it again. My divergence theorem says divergence of the vector field, volume integral of that over the given volume nu is equal to the surface integral over the surface enclosing the volume nu. Try to understand it. This is my volume, enclosed volume. It has surface, it has 6 faces. So I will find first my left hand side. That means I will find divergence of the vector field and given vector field, and I will integrate that over the volume enclosed by this cube. Then I will evaluate surface integral. Then I will see my left hand side and right hand side values will be same. That will verify my theorem. So I will give name to the 6 faces of the cube, right? I name this front face, change the color. I name this front face as face 1 first, back face as second, right face as third, left face as 4, upward face as 5th, and downward face as 6. So front face is first, back face is second, right face is third, left face is 4, up face is 5th, and downward face is 6. Okay, now we move to the solution. Now solution is like this. Try to understand it. So I first find the divergence. Then I have to find dou by dou x of vx plus dou by dou y of vy plus dou by dou z of vz. Dou by dou x of vx. What is vx? Vx is y square. I have to write dou by dou x of vx, which is y square. Dou by dou y of vy. What is vy? 2xy plus z square plus dou by dou z of vz. Vz is 2yz, right? Dou by dou x of y square plus dou by dou y of 2xy plus z square and plus dou by dou z of 2yz. What is this? Y square is constant with respect to x, so its derivative is 0. Dou by of this. The second term will give me 0. First term I am differentiating with respect to y, so it is 2x. Dou by dou z of 2yz, I am differentiating with respect to z, so it is 2y. You can write it, 2 can be taken as common, 2 into 2 times x plus y. So I have found the value of divergence, right? Now I will find my volume integral. What was volume integral? I have to find divergence of the vector field. Then I have to find this volume integral. See, I put the value of the divergence, that is 2 times x plus y. Then it is my volume integral. Then here it is d tau. Now d tau is actually what? D tau is infinitesimal volume element, that is product of three things, dx, dy and dz, right? So it will become 2 can be taken outside the integral. Then I have three integrals actually. Then I have x plus y, then I have dx, dy, dz. Now limits on the integral are 0 to 1. Because if you see, you constructed this cube, its one face is located at the origin. Then you have to move along x from 0 to 1 to complete the whole volume, to incorporate the whole volume into the integral. You have to give limit on x from 0 to 1, y 0 to 1, and on z 0 to 1. So it will be 0 to 1, 0 to 1, and 0 to 1, right? Now we have to evaluate this integral. How we evaluate this integral? We first evaluate this much, right? Then that answer we put in the second integral, evaluate this integral. Then that answer is placed in the third integral, evaluate this thing. We get the answer, right? So when you evaluate this, you try it. This integral after solving will give us 2. Actually this whole integral will be 1, but outside we have 2. So this is 2. Check it. Check it at home. So this is your assignment. This will give me 2. Thus I have found the left hand side of the divergence theorem. Left hand side is divergence of V, this volume integral. This is 2. This is my left hand side, right? Now move to the right hand side. Now right hand side is what? Closed integral V dot dA over the surface. Now my surface has 6 faces. So I find flux for phase 1, phase 2, phase 3, phase 4, phase 5, phase 6 and add those. That means it can be written as V dot dA first. That means phase 1. plus v dot dA phase second plus integral v dot dA phase third plus integral v dot dA phase four plus integral v dot dA phase 5 plus integral v dot dA phase 6. So I will find term wise, then add all 6 terms to get my right hand side. Follow me. So first phase, integral v dot dA. What is that? Now see, my move the diagram first. This is my first front face. This front face lies in the YZ plane. Therefore, its area element will be dy and dz, and that is pointing along positive x direction. Positive x direction means this area element dA will be dy dz I cap, because I is a unit vector pointing along positive x direction. I have to dot with the I cap, that means x component of v, which is y square, right? So if I write it here, for first phase v dot dA is 0 to 1. See, I am evaluating the surface integral, that's why there are only two integrals. Y square dy dz. Where from I have obtained it? Y square is the x component of the vector field. dA was pointing along positive x direction, so I have to dot it with that. dA is dy dz I cap. I have to dot it with x component of v, which is y square. So I have done it, and limits on y and z are 0 to 1, because cube is placed at the origin, and I have to move from 0 to 1 along y direction and 0 to 1 along z direction. When I solve this integral similarly, first I evaluate this piece, then this piece. When you do that, this will be equal to 1 by 3. Check all these things. Don't trust me, evaluate. It will be 1 by 3. Then I have second phase. V dot dA for second phase. It will be 0 to 1, 0 to 1. Now I will have minus here, y square dy dz. Can you tell me why this minus? See why this minus. Second phase is back phase. It is also in a YZ plane, yeah, parallel to YZ plane. So area element will be dy dz, but it is pointing, because area vector is to be taken as outward normal, it's pointing along negative x direction. Negative x direction means minus I cap will be attached to it. Then I have to dot with x component of v, which is y square, right? That's why this minus. So I have minus 0 to 1, 0 to 1, y square dy dz. Again, when you solve it, it will be minus 1 by 3, right? Then third thing, v dot dA 0 to 1, 0 to 1, 2xy plus z square dx dz. Now why so? Move to the figure. My third face is this face. And this face is parallel to xz plane. That means its area element will be dx dz, right? Dx dz. That's why here I have written dx dz, right? Then this area element is pointing along positive y direction, that is plus j. So I have to dot it with j component, the y component of vector field, which is 2xy plus z square. So this is why I have written here 2xy plus z square. Another thing, for this area, y is 1. Y is 1 because this third face is located at y is equal to 1 coordinate. So when you put that y is equal to 1 here, it will become simply what? 0 to 1, 0 to 1, y1, it is 2x plus z square dx dz. 2x plus z square dx dz. Now evaluate this integral, it will be 4 by 3. 4 by 3, right? We have done 3 faces, now we have 4th face. 4th face is simple. Integral v dot dA, it will be 0 to 1, 0 to 1 z square dx dz and minus. Now see how. Now we are talking of 4th face. Go to the figure. This is my 4th face. It is in parallel to xz plane. There will be dx dz, right? It is pointing along negative y direction, right? Negative y direction means this, right? Negative y direction means minus j. So that's why there is minus in the integral. I have to dot it with this component, but it is located at the place y is equal to 0. This face is located at y is equal to 0. When I put y is equal to 0, this term becomes 0. So only z square remains in the integral. So only z square remains in the integral, right? So when you evaluate this integral, it will be minus 1 by 3. And y is 0 for this piece. Then 5th piece is v dot dA. It will be 0 to 1, 0 to 1, 2yz dx dy. See how? 2yz dx dy. See how? 5th face. Go to the figure. This is my 5th face. It is parallel to xy plane, so its area element will be dx dy. It is pointing upward. Upward is positive z direction, so I have to dot it with 2yz, and it is located at z is equal to 1. So there will be only 2y in the integral. C. It is 2yz dx dy, but z is 1. It will be 0 to 1. So 0 here. 0 to 1. 0 to 1. Z is 1. That will be 2y dx dy. Solve this integral, it will be 1. Now last piece, sixth, which is integral v dot dA. It is minus 0 to 1, 0 to 1, 2y z dx dy. Why minus? Because now it will be pointing along negative z direction. Now z is 0 for the sixth piece. So when you put z is equal to 0 in this integral, 0 to 1, 0 to 1, 2y z dx dy, it will be 0. Now I add all the 6 values to get my right hand side. That means the right hand side of my divergence theorem is 1 by 3 minus 1 by 3 plus 4 by 3 minus 1 by 3 plus 1 plus 0. 1 by 3 minus 1 by 3 plus 4 by 3, first piece, second piece, third piece, minus 1 by 3 plus 1 plus 0. Adding these values is simply 2. So left hand side is equal to right hand side. Hence the theorem is verified. Now similarly, we will do a question at home. I have a question for you. Homework. The homework is test the divergence theorem for the function. What is the function? V is equal to xy I cap plus 2y z g cap plus 3 zx p cap. Take as your volume the cube shown in figure A with the sides of length 2. So I have to draw a figure. So my figure is this x, this y, this z. Let me take another color, yellow. Looks dim. choose another color, black. Right, again I have a cube. Now difference is your coordinate is 2, your coordinate is 2, your coordinate is 2. This is my figure A. That means this is a cube. It's my x direction, y direction. This is z here, not 2. 2 is the coordinate here, right? So it has length, edge length of 2. Cube with edge length of 2. That's why coordinates are 2, 2, 2. The question says test the divergence theorem for the function. I am given a vector field. Its x component is xy. Its y component is 2yz. Its z component is 3zx. Take as your volume the cube shown in figure A. This is my cube with the sides of length 2. The same question which I have solved with you. A vector field is different, cube is different. Procedure is same. You have to first take the left side of divergence theorem. What is that? That is the volume integral you have to solve. You have to first find the divergence of V. Then you have to evaluate the volume integral. That will be your left hand side. That will be your left hand side. Then you divide the surface into 6 pieces as we have done in the example. First, second, third, fourth, fifth, and sixth. Then you add those pieces to find this surface integral. That will be your right hand side of the divergence theorem. When you do that, the left hand side must be equal to the right hand side. Right? This is all for today. Thank you. Work hard and God bless you. Assalamu alaikum.